This is the data handbook table. These values shows for journal bearings. These are the machinery types. These are the application of bearings in different machineries, and this column shows type of bearing. This column shows maximum bearing pressure, and this column shows absolute viscosity. Here the absolute viscosity in kg per meter second. Okay, here this value is bearing characteristic number, that is Zn by P. This value in Newton per mm square. Okay, P bearing pressure in Newton per mm square, Z in kg per meter second. The total units for Zn by P is no units. Zn by P is a dimensionless number. Okay, there is no units for Zn by P. Okay, here C by D is the diametral clearance ratio. Okay, and this one also no units, and L by D is the length and diameter ratio. This one also no units. Okay, yeah, these are the applications. By using type of application, you have to consider the values: bearing type, maximum pressure, absolute viscosity, Zn by P values. Okay, this is the example for centrifugal pumps. The type of bearing is rotor type, and the maximum bearing pressure is 0.7 to 1.4 Newton per mm square, and absolute viscosity is 0.025. Okay, and the Zn by P bearing characteristic number is 28. C by D ratio is 0.0013, and L by D is the ratio of L by D equal to 1 to 2. Okay, now these are the design procedure for journal bearings. Okay, for design of journal bearing, the following procedure may be adopted in design. When the bearing load, the diameter and speed of the shaft are known. Okay, this is step one. In step one, first of all, you have to find the value of L by D ratio from data handbook. Okay, so by using data handbook, you have to find the value of L by D ratio. Okay, and in step number two, you have to check the values of bearing pressure. Okay, you have to check the value of bearing pressure. So here the formula for bearing pressure, P equal to load by area, where W is the load on journal, L is the length of a bearing, D is the diameter of a shaft. Okay, from data handbook you have to check the value. Okay, now in step number three, you have to identify the type of lubricant. You have to identify, or you have to select a suitable type of lubricant for journal bearing. The example for lubricants is SA10, SA20, SA30. These are the types of lubricants. Okay, these are the types of lubricants used in journal bearings. And in step number four, you have to find the value of Zn by P. Okay, from data handbook you have to choose suitable Zn by P value. Okay, you have to check with that value. In step number five, you have to find the value of C by D ratio from data handbook. In step number six, you have to find the value of coefficient of friction, that is mu. Okay, mu is the coefficient of friction. There is no units for coefficient of friction. The formula for coefficient of friction for general bearings, mu equal to 33 by 10 power 8 Zn by P. Okay, Zn by P into D by C plus K. This is the formula for coefficient of friction. Okay, here the value of z in kg per meter second, and n is the speed of a shaft, that is in rpm. P is the bearing pressure in newton per mm square. Okay, these are the important. Here, Z is the bearing. Here, absolute viscosity of the lubricant. Z is the absolute viscosity of the lubricant. Okay, this is very important for journal bearings. Okay, here small k is the end leakage factor. Okay, here for L by D ratios of 0.75 to 2.8, the value of k equal to 0.002. Okay, you have to consider this value for L by D ratios 0.75 to 2.8. In step number 7, determine the amount of heat generated by using formula Qg equal to mu Wv. Okay, this is the formula for amount of heat generated. Here, uh, here Qg means amount of heat generated, and mu is the coefficient of friction. There is no units for friction, and W is the load on shaft. The units for load is newton. Okay, and V is the velocity of the shaft. So velocity of the shaft or velocity of the journal. So here the formula for velocity V equal to pi d n by 60. Okay, velocity v equal to pi dn by 60. Okay, d small d is here, d is the diameter of a shaft. Okay, pi d n by 60. N is the revolution speed of a shaft in rpm. Okay, by using this formula, you have to find the value amount of heat generated in journal bearing, and the units for heat generation equal to watts. Okay, watts or joule per second or newton meter per second. Okay, these are the units for heat generation. In step number 8, you have to find the amount of heat dissipated by lubricant. Okay, you have to find that value, because this is because heat dissipation means amount of heat cooled by given lubricant. Okay, this is the formula for amount of heat dissipation. Here C A into TB minus TA. Here C is the coefficient of heat dissipation. Capital C is the coefficient of heat dissipation, and capital A is the area of a projected area of a bearing. Okay, that is the L, length of a bearing, into small d, diameter of a shaft. Okay, capital A equal to L into D. Now TB means bearing surface temperature. TB means bearing surface temperature. TA is the ambient temperature. TA is the ambient temperature. And here, if bearing temperature is not given, then operating temperature of the lubricant will given. Okay, so by using this formula, you have to find the amount of heat dissipation. Okay, the units for amount of heat dissipation is also same for heat generation. Okay, units are same for both cases. In step number 9, this is the last step. In step number 9, you have to find the value of mass of lubricant oil required for artificial cooling. Okay, this is the formula for mass of lubricant oil required for artificial cooling. M equal to Qt by S into T. Okay, Qt is the difference between amount of heat generation minus amount of heat dissipation. Okay, formula for Qt equal to Qg minus Qd. So Qg already in step number 7, Qd is in step number 8. Okay, by using this formula, you have to find the value of Qt, and then after you have to substitute the value of S. S is the specific heat of oil. Okay, its value may be taken as 1840 to 2100. Okay, now T is the small t is the rise of temperature. By using these 9 steps, you have to design a journal bearing. Okay, this is the given question. In this question, uh, here design a journal bearing. So you have to design a journal bearing, and the application of journal bearing is given. That is, the application is in centrifugal pumps. Okay, so bearings are used in centrifugal pumps for this problem. So you have to consider this type. Okay, from data handbook you have to consider values for centrifugal pumps. Okay, here the diameter of the journal is given. That is, a diameter of the journal means small d. Okay, small d is given, and load on the journal also is given. Load on the journal means W, capital W. Okay, W is the load on shaft. Okay, now speed of the journal also is given. That is, a speed equal to N, capital N. Capital N is the speed of a shaft. Okay, these are in revolutions per minute. And type of lubricant also is given. The type of lubricant is SAE 10. Okay, and here uh, for which the absolute viscosity at 55 degrees Celsius is also given. That is a 0.017. Okay, 0.017 is given. That is a Z. This value is Z. Absolute viscosity is in kg per meter second. Okay, absolute viscosity equal to 0.017. Okay, this is for Z. And here the 55 degrees Celsius is the uh, operating temperature. Okay, operating temperature 55 degrees Celsius is the operating temperature, and ambient temperature of the oil is 15.5 degrees Celsius. That is TA. This value is TA, and maximum bearing pressure is given. That is W is also given. That is load by area, length into diameter of a shaft. Okay, this value is given. P equal to 1.5 Newton per mm square, and heat dissipation coefficient, that is C. This value is capital C. C equal to 1232. Okay, and also calculate a mass of lubricant oil required for artificial cooling if rise of temperature of the oil be limited to 10 degrees Celsius. Okay, by using these values you have to design a journal bearing. Okay, now given data is diameter of the journal. So it is in mm. So in meters, 100 by 1000 equal to 0.1 meter. Okay, now load on journal also is given. That is W. Speed of the journal N equal to 900 rpm, and type of lubricant equal to SAE 10. Absolute viscosity, that is Z, is given. This is the bearing operating temperature. Okay, operating temperature equal to 55 degrees Celsius. So this is 55 degrees Celsius. Operating temperature equal to 55.5 degrees Celsius. Okay, and ambient temperature also is given. That is a TA. TA equal to 15.5 degrees Celsius. Maximum bearing pressure for pump is also given. There is a P equal to 1.5 Newton per mm square. And rise of temperature of oil is also given, that is T, small t equal to 10 degrees Celsius. And the heat dissipation coefficient also is given, that is capital C equal to 1232 1232 watts per meter square per degree Celsius. Okay, this is the data handbook values. From given data, already we know that the application of a given journal bearing is in centrifugal pumps. So you have to consider these values for our design purpose. Okay, so in this problem you have to consider Z value. Don't consider Z value. Okay, these values are already. Okay, you have to consider only bearing characteristic number, that is Zn by P. Zn by P equal to 28 and C by D ratio equal to 0.0013 and L by D ratio equal to 1 to 2. Okay, you have to consider these three values. Okay, now Now, coming to the design procedure, step number one. In step number one, you have to find the value of length of a bearing. That is, you have to find the value of L. Small l is the length of a bearing. So, by using data and work, you have to consider L by D ratio. Okay, from data and work, you have to find the value of L by D ratio for centrifugal pumps. Yeah, small d, diameter of the journal is given. That is the diameter of the journal equal to 100 mm is given. So therefore, from data and book for centrifugal pumps, uh, this is a data book for centrifugal pumps. Uh, C by D, L by D, C by D ratios and L by D ratios. This is Zn by P ratio. So you have to consider first, in first step you have to consider L by D ratio. This is a L by D ratio, that is a 1 to 2. Okay, so you have to consider these two limits. Okay, so L by D ratio for centrifugal pumps varies from 1 to 2. So you have to consider between 1 to 2. So here let's take L by D ratio to 1.6. This value 1.6 is lies between 1 and 2. So here I consider 1.6. Okay, length of bearing. So therefore length of a bearing equal to uh, 1.6 into D. From this formula, L equal to 1.6 into D. So the length of the bearing equal to 160 mm. This is the answer for step 1. So from this step, we got the value of length of a bearing, that is L. L equal to 160 mm and diameter D equal to 100 mm. Okay. In second step, you have to find the value of bearing pressure. Okay. In given data, already the value of bearing pressure already is given, but you have to check with values. Okay, in given data the bearing pressure is given, that is P equal to 1.5. This value is maximum. Okay, by substituting the length of a bearing and diameter of a shaft, you will get another bearing pressure, that is bearing pressure P equal to load by L into D, where W equal to 20 newtons, 20,000 newtons. By substituting these values, bearing pressure P equal to 1.25. Okay, this is the working pressure. Actual working pressure is 1.25. Okay, this 1.25 value is working pressure or design pressure. This value is less than the given maximum pressure. Okay, the given maximum pressure is 1.5. So within the limits. Okay, so the generated bearing pressure is less than the maximum pressure. So these the values of length and diameter of a bearing are in safe zone. Okay, in step number 3 you have to select a suitable lubricant type, but in this question already we have from already we know that the type of lubricant is SC10. Okay. In step number 4, you have to find the value of Zn by P. Okay. First of all, you have to substitute values from given data. You have to substitute values. Then after you got Zn by P equal to 12.24. But you have to consider from data handbook. Okay. For centrifugal pumps, from data handbook for centrifugal pumps, Zn by P equal to 28. You have to compare with this value. So uh, from data handbook, Zn by P equal to 28. But from our values, the value of Zn by P equal to 12.24. You have to compare these two values for identifying the type of lubrication system. Okay. So the minimum value of the bearing modulus at which the oil film will break is given by 3K equal to Zn by P. Okay. So bearing modulus at the minimum point of friction, you have to substitute values of Zn by P. You have to substitute the value of Zn by P obtained from data and book. Okay. This value you have to substitute 28. So here the value of K equal to 1 by 3 into Zn by P value is 28, then K equal to 9.33. So this value 9.33 value is less than the our value 12.24 value. So since the calculated value of bearing characteristic number Zn by P equal to 12.24 is more than the value of 9.33. So therefore the bearing will operate under a hydrodynamic condition. Okay. By using these two values, we conclude the type of lubrication, that is a hydrodynamic condition. Okay. Here in step number 5, from data and book, we have to find the suitable clearance ratio, diametral clearance ratio, that is C by D. You have to consider C by D ratio. From data and book, the value of C by D for centrifugal pumps equal to 0.0013. Okay. From this value, you have to consider C by D equal to 0.0013 for centrifugal pumps. Okay. This is the answer for step number 5. In step number 6, you have to find the value of coefficient of friction, that is mu. Here mu is the coefficient of friction due to bearing rubbing surfaces. The formula for coefficient of friction mu equal to 33 by 10 power 8 Zn by P into D by C plus small k. Here small k is the end leakage factor. Okay. For L by D ratios of 0.75 to 2.8, the k value is 0.002. Okay, you have to consider this value k equal to 0.02 for L by D ratios of 0.75 to 2.8. Okay, here Z value, the value of Z always in kg per meter second, and N value in RPM, P value in Newton per mm square. Okay, so from previous steps, you have to substitute these values. Okay, 33 by 10 power 8 into Zn by P. The value of Zn by P is obtained from our substitution values. So Zn by P value equal to 12.24 into D by C. Okay, from from step number 5, the value of C by D equal to 0.0013, but this is a D by C is the reciprocal of this value. So 1 by 0.0013 for D by C plus K equal to 0.002. Okay. So the final answer for coefficient of friction mu equal to 0.0051. Okay, there is no units for coefficient of friction. Okay, no units for coefficient of friction, so it is a dimensionless number. Mu is a dimensionless number. So the answer for coefficient of friction is mu equal to 0.0051. Now coming to the step number 7, in this step you have to find the amount of heat generation. Amount of heat generated due to friction. You have to find that value by using general empirical formula Qz equal to mu Wv. This is the formula for amount of heat generated. So here mu is the coefficient of friction. Already this value is obtained in previous step number 6. Okay, and W is the load on the shaft or load on the journal. Okay, this value also is given, that is 20,000, and V is the velocity of the shaft, that is V equal to pi dn by 60. Okay, now mu equal to coefficient of friction 0.0051 is obtained from previous step number 6. Okay, and W equal to 20,000, and V is the velocity of the shaft, that is pi dn by 60. Here D is the diameter of the shaft, that is 100 mm. You have to substitute diameter in meters. Okay, because the velocity in meter per second. Okay, that's why you have to consider diameter in meters. Now speed is in 900 rpm. So by substitute these values in this formula, you can get the value of qz equal to 480.7 watts. Okay, this is the answer for amount of heat generated due to coefficient of friction. Okay, now coming to the other step, step number 8. In step number 8, you have to find the value of amount of heat dissipated. Okay, in this step, we can find the amount of heat cooled due to lubrication. Okay, this is the formula for amount of heat dissipated in a bearing. Qd equal to amount of heat dissipation, and C is the dissipation coefficient. Okay, capital A is the area of a projected area of a shaft, and Tb is the bearing surface temperature, Ta is the ambient temperature. Okay, now if Tb value is not given, then you have to use T naught. T naught is the operating temperature minus Ta by 2. This is the formula for heat dissipation. The units for heat dissipation is watts or joule per second. Okay, now substitute the values from given data. T naught value is given, that is 15.5 degrees. Sorry, this value is 55. This value is 55.5. The operating temperature is 55.5 degrees Celsius, and the ambient temperature is Ta equal to 15.5 degrees Celsius, and the heat dissipation coefficient is 1 to 1232 watts per meter square per degree Celsius. These three values are given in question. So by using these three values, you have to substitute these three values. You can get the value of heat, amount of heat generated, amount of heat dissipated. So the amount of heat dissipated here, TB is not given. Okay, bearing surface temperature is not given. Instead of TB, T naught is given. That is T naught equal to 55 degrees Celsius, and Ta is the 15.5 degrees. By substitute these two values, you can get the value of Tb minus Ta, or 1 by 2 T naught minus Ta. So, and then after you have to substitute the values of C and capital A. Capital A is the area. Uh, Here capital A equal to length of a bearing into diameter of a shaft. In step number 1, we got length of a bearing, that is 160 mm, and the small d is the diameter of the shaft. Okay, diameter of shaft is given in problem. So d equal to 100 mm and l equal to 160 mm, but you have to consider these two values in meters. Okay, so that's why l equal to 160 mm equal to 0.166, and d equal to 100 mm equal to 0.1 meter. Okay, so by substitute these two values, we got the value of qd. The final answer for amount of heat dissipated equal to 389.3 watts. Okay, now amount of heat dissipated equal to 389.3. Eh, now from step number 7 and step number 8, we got a value of amount of heat generated and amount of heat dissipated. So here the amount of heat generated equal to 480.7 watts, amount of heat dissipated equal to 389.3 watts. Okay, you can observe here the amount of heat generated is more than the amount of heat dissipated. So the the amount of generation is greater than the amount of heat dissipated. So that's why you have to provide an artificial cooling. Okay, because heat is here, the heat is, the amount of heat generated is more than cooling. That's why you have to supply artificial cooling for cooling remaining temperature. Okay, so the balancing or remaining temperature equal to remaining amount of heat equal to amount of heat generated minus amount of dissipated equal to 480.7 minus 389.3. You got qt equal to 91.4 watts. This is the uh, amount of heat amount of heat amount of amount of artificial cooling required for cooling this temperature. Okay, now in last step, that is step number 9, you have to find the mass of artificial cooling required. So here m is the mass of the lubricating oil required for artificial cooling in kg per second. Okay, the formula for mass equal to qt by st. Already in previous step, already we got the value of qt. So qt equal to uh, here the value of qt equal to 91.4 watts. So you have to substitute that value qt. So qt equal to that 98 point value, and 90, and S is the specific heat of oil. So the specific heat of oil is 1840 to 2100. You have to consider within these two values. Okay, and the rise of temperature small t value is also given. Here I consider S equal to 1900. Okay, here I consider a value of S equal to 1900 and T equal to 10 degrees. T rise of temperature 10 degrees is given in question. So the final answer for the mass of lubricating oil required for artificial cooling M equal to 0.288 kg per minute. Okay, this is the final answer for question. Okay, once again I repeat the design procedure of journal bearing. Okay, in first step you have to consider the value of L by D ratio. Okay, from data handbook you have to consider the value of L by D ratio. Okay, and similarly in step number 2 you have to consider or you have to check the bearing pressure P. Okay, the formula for bearing pressure P equal to W by L into D. Here W is the load on shaft, L is the length of the bearing, D small d is the diameter of the shaft. Okay, by using these values, you have to find the value of bearing pressure P. Okay, and in step number 3, you have to select a suitable lubricant type. Okay, yeah, SE10, SE20, SE30. These are the examples for bearing types. In step number 4, you have to determine the value of Zn by P. Okay, here Zn by P is a bearing characteristic number. Okay, Zn by P is the bearing characteristic number. It is a dimensionless number. So dimensionless number means there is no units for Zn by P. But here the value from data and book also you have to find the value of Zn by P from corresponding application of bill. Okay, and in step number 5, you have to choose a suitable diametral clearance ratio. Okay, C by D is the diametral clearance ratio, where uh, C is the diametral clearance and small d is the diameter of the shaft. Okay, so from data and book, you have to select the C by D ratio. This is the step number 5. In step number 6, you have to select a suitable. Sorry. In step number 6, you have to find the value of coefficient of friction, mu. Okay. By using this formula, you have to find a value mu. Okay. Here mu also a dimensionless number. That is no units for coefficient of friction. Okay, here Z always first here you have to remember Z always in kg per meter second, speed n in rpm, and bearing pressure in Newton per mm square. These are the units. Okay, these are the important units to substitute in this equation. Okay, here small k is the end leakage factor. The value of end leakage factor for L by D ratios 0.75 to 2.8 is k equal to 0.002. Okay. In step number 7, you have to find the value of amount of heat generated. Okay. So by using this formula, you have to find the value of amount of heat generated. In step number 8, you have to find the value of amount of heat dissipated. Okay. In step number 9, you have to find the value of amount of heat. Sorry. In step number 9, you have to find the value of amount of artificial cooling required. Okay. Mass of artificial cooling required. Here mass m in kg per second. Okay, where Qt is equal to difference of heat generation and heat dissipation. S is the specific heat of the lubricant oil. Uh, Usually, the value for a specific heat is 1840 to 2100 joule per kg per degree Celsius. Okay, and T is the rise of temperature. So, by using these 9 steps, we have to consider. Okay, so this is the data and book table. So by using this data and book, you have to consider values of Zn by P, C by D ratios, and L by D ratios. Okay, in present problem, I consider the values for centrifugal pumps. So for centrifugal pumps, I consider 28 for Zn by P bearing characteristic number, and 0.0013 for C by D ratios, and 1.6 here I consider 1.6 for L by D ratios. Here 1.6 lies between 1 and 2. So these are values I consider. Okay. Okay, friends. In next class I will explain some more problems. Okay.